A blessed day, everyone. I am Erilikas Piroaya, a Bachelor of Science in Mining Engineering student at St. Paul University, Surigao. So in this video, I am going to show you solutions to non-exact differential equation. This is a video project in our differential equation subject to be submitted to our instructor, Mr. Jenny C. Cano.
So, I have here the given differential equation, which is y ln y dx plus x minus ln y dy equal to 0. As we can see, this differential equation is an example of a non-exact differential equation. So we are going to solve for the solution by determining the integrating factor. Before I will proceed in solving the given differential equation, let me do some recap in solving this type of differential equation, which is a non-exact differential equation. So, how do we differentiate non-exact differential equation? So, a non-exact differential equation is a differential equation in form m function xy dx plus n function xy dy equal to 0. If the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x, then the differential equation is said to be a non-exact. If the given differential equation is not exact, then make that equation exact by finding the integrating factor. In non-exact differential equation, so the idea is that we are going to determine an integrating factor, so that would make a non-exact differential equation into exact. Then, an integrating factor will be multiplied with the original differential equation. And once we multiply it, then we are going to test its exactness if it becomes a non-exact differential equation. Then we can be able to find its general solution. So, there are methods in finding the integrating factor for the given non-exact equation. So, as we can recall, there are different cases in determining an integrating factor of a non-exact differential equation. But in this video, I will present two cases only, intended for us to choose what case to use in this given non-exact differential equation. So first, for case 1, which is a raised to the integral of the difference of the partial derivative of m with respect to y and partial derivative of n with respect to x over n dx. So we can say that it belongs to case 1 if it is a function of x only, or it yields the function yields in x alone. So for case 2, which is a raised to the integral of the difference of the partial derivative of n with respect to x minus to the partial derivative of m with respect to y over m dy. We can say that it belongs to case 2 if it is a function of y only, or it yields in y alone. So this is the methods in finding the integrating factor for given an exact equation. So we have here also the methods in solving non-exact differential equation. So this is the sequence in solving a non-exact differential equation. So first step, we are going to test for non-exactness by ensuring that the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x. So once we can conclude that the given differential equation is not exact or non-exact, Then we are going to proceed for the next step, which is to find the integrating factor. Then if it not exact, identify the equation. If it falls under case 1 or case 2, then we are going to solve for the integrating factor. So the next step is we are going to multiply the integrating factor to the original differential equation. Then we will verify for exactness. Then if it becomes exact, the differential equation becomes exact, then we can now solve for the general solution. So without further ado, we are going to solve for the given differential equation, which is y ln y dx plus x minus ln y dy equal to 0. So for the first step, we are going to test for non-exactness. So we will first determine the m function. Our m function here is equal to y ln y, and our n function here is equal to x minus ln y. Then we are going to find its derivatives. So the derivative of m function will become the partial derivative of m with respect to y is equal to ln y plus 1. Then for our n function, it will become the partial derivative of n with respect to x equal to 1. So we can now see if it an exact or a non-exact. It is very obvious that the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x. So we can now conclude that this is a non-exact differential equation. Since this is a non-exact differential equation, let us proceed for the second step, which is to find the integrating factor, so that would make the differential equation an exact equation. So this is case 1 and case 2. So in order for us to determine where the differential equation belongs, whether case 1 or case 2. So let us now, we have here our derivatives of partial derivative of m with respect to y and partial derivative of n with respect to x. So we are going to substitute it here for case 1. So our partial derivative of m with respect to y minus the partial derivative of n with respect to x, we will substitute it. It will become ln y plus 1 minus 1 all over n. Our n here is x minus ln y. This is our n, and we are going to put it here, and we are going to solve it, and it will result to ln y over x minus ln y. So as we can see, the result did not yield in y alone or in x alone. So let us proceed and let us test it in case 2, which is the difference of the partial derivative of n with respect to x and the partial derivative of m with respect to y all over m. So let's substitute. It will become 1 minus ln y plus 1, and our m here, which is this y ln y, we'll put it here and we'll solve for it, and it will result to negative ln y over y ln y, and it will result to negative 1 over y. So we can now see that the given differential equation falls to case 2 because it yields, the function yields in y alone. So this is the case 2 we are going to use in solving for the integrating factor. So this is the formula for finding the integrating factor, which is mu is equal to a raised to the integral of the difference of n, the partial derivative of n with respect to x, the partial derivative of m with respect to y over m dy. So we will substitute this given negative 1 over y here. It will become a raised to the integral of negative 1 over y dy. So we will find the integral of negative 1 over y, and it will result to a to negative ln y, and we will solve further, and it will result our integrating factor here will become mu equals to 1 over y. So this is now our integrating factor. Since we have our integrating factor, we can now proceed to the third step, which we are going to multiply the integrating factor to the original differential equation. So we are going to multiply this, our integrating factor, to the original differential equation. So it will become 1 over y multiplied to y ln y dx plus 1 over y multiplied to x minus ln y dy. Then it will our 1 over y multiplied to y ln y will become ln y dx, and our n function will become x over y minus ln y over y dy. So this is now our new differential equation. Since we have our new differential equation, let us proceed in testing its exactness, if it is an exact equation, so that we can proceed to the last part, which we are going to find the general solution. So now we are going to use our new differential equation. Then we will determine our m function. Our m function here is ln y, and our n function here is x over y minus ln y over y. Then we are going to find its derivatives. It will become the partial derivative of m with respect to y is equal to 1 over y. For the n function, the partial derivative of n with respect to x is equal to 1 over y. So as we can see, they are now the same. So we can conclude that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So we can now conclude that this is an exact differential equation. So we can now proceed for the step 4, which is the last step in solving this differential equation. We are now going to solve for the general solution. So we now use our new differential equation. So it will become the integral of ln y dx plus the integral of x over y minus ln y over y dy equal to 0. So solving, the integral of ln y dx will become x ln y, and the integral of x over y minus ln y over y will become negative 1/2 multiplied to ln y raised to the second power equal to the constant. So this is our general solution, but we are going to simplify it further. So simplifying, we have here x ln y minus 1 over 2 ln y raised to the second power equal to the constant. So we are going to multiply negative 1/2 to ln y raised to the second power. It will become negative ln y raised to the second power all over 2. So solving further, we are going to simplify ln y raised to the second power. It will become ln squared y all over 2. Then we have here our general solution, which is x ln y minus ln squared y over 2 equal to the constant. So this is now our solution. So that is all for this video. This is a video report project submitted by yours truly, Eril Ligas-Piroaya, a second-year Bachelor of Science in Mining Engineering student, submitted to Mr. Jenny C. Cano, a licensed professional teacher PhD, a mathematician, professor, and educator. Thank you so much for watching this video, and may God bless us all. Once again, I am Eril Ligas Peroaya. Thank you.